My dear student, today let us discuss about the nature of the fixed point. According to the nature of the eigenvalues of the characteristic equation, how the nature of the fixed point is determined, and this is very important. For the linear system, we already know that origin is always a fixed point, and also we have find out the equation of the characteristic equation and the roots of the characteristic equation. So for a given for a given linear system, so for example, for a given linear system, dx by dt, this is equal to ax plus by, and dy by dt, this is equal to cx plus dy. So the matrix of the coefficient is equal to a, b, c, d. This is the matrix. So characteristic equation of this matrix is given by lambda I square a plus d minus lambda I square lambda I square minus lambda I square minus a plus d, where a plus d is the trace of the square matrix, plus ad minus bc. Ad minus bc is the determinant of the square matrix. Okay, then roots are given by this formula, and so everyone knows it. So this is trace a, this is trace square minus 4 times determinant a. So if trace square minus 4 times determinant a is positive or 0, the roots are real. Okay, the roots are real. So that means what? Lambda 1 and lambda 2 are real. Lambda 1 and lambda 2 are real. So in that situation, suppose if lambda 1 and lambda 2 are greater than, the fixed point is called unstable knot. Okay, the fixed point is called unstable knot. Why? Let us see why it is like this. So let me go back to this one. Yeah, another, let us open. So what is the equation? So root is, the solution is given by, yesterday we have talked about that one. Solution is given by x is equal to, say, a, capital A, e to the power lambda 1 t plus capital B, where a, b are constant, depend upon initial condition. So e to the power lambda 2 t. Okay, so then y is equal to, this is equal to c e to the power lambda 1 t plus here also d e to the power lambda 2 t. So if if lambda 1 is positive, lambda 2 is also positive, and then as t tends to infinity, this quantity tends to infinity, and this quantity is also tending toward infinity. All right, so similarly, when lambda 1 lambda 2 are positive, then y tends to infinity as t tends to infinity. So what is the situation in the phase curve? What is the situation in the phase curve is like this. I'll give you example. I will draw in the software. So it will be as t tends to infinity, both the variable x and the y, this is x, this is y axis, and this is x axis. Both the variable x and y are tending toward infinity. Okay, so that means this is the fixed point, origin is the fixed point, both are going away from the fixed point. Okay, both are going away from the fixed point. Along the axis it is like this, along the axis it is like this, it is going away. So point here, point here, so it will be going away like this. Point here like this. Point here, it is also like this. It will be some curve going away. Point here, it will be moving away. So both are, as t tends to infinity, y is also tending toward infinity, x is also tending toward infinity. Okay, so here also it is going like this. So moving away from the, the orbit or trajectory or the phase curve, is moving away from the origin, from the fixed point. So that is why it is called unstable. So unstable, okay, that is why it is called unstable, right? So see, yeah, so if lambda 1 lambda 2 are, so that is the characteristic root. If lambda 1 lambda 2 are positive, then the fixed point is called unstable knot. And so conversely, or in another way, if both lambda 1 and lambda 2 are, negative, the fixed point is called stable knot. So just in this case, just the opposite happens, okay, the earlier case. So for positive one, it is moving away. For both are negative, then it is moving in this direction, okay, it will be moving in this direction, right? So that is why, any point, if you start from here, its orbit moving toward the fixed point. If you start from here, its orbit is moving toward the fixed point like this, okay. So that is why this fixed point is called a stable fixed point or a stable knot in this situation. So if the characteristic roots are both negative and real, then the fixed point is called a stable knot. The fixed point is called stable knot, okay. So then the another one is like this, it may happen like this. One is negative, another one is positive, okay. One is negative, another one is positive. So in one way, it is in that situation what happened. In that situation what happened, let us see. In that situation, in one direction it is coming toward the fixed point, in another direction it is moving away, okay. So it will be, situation will be like this. So suppose this is the phase space, this is x-axis, this is y-axis. So in one direction it is, moving in. So suppose x-axis, it may be it is moving away, but in the y-axis it is moving out from here like this. So what happened, if you start from here, so as t tends to infinity, y is moving toward the infinity, but x is speed. So this curve is very close to this y-axis, mean x component is tending toward 0, but whereas it is going away, this means as t tends to infinity, y is tending toward the infinity like this, okay. So like this, you will see, we'll draw it like this, or from here it is like this, okay. So if it is the initial point, its orbit is like this, okay. So here also it will be like this, all right. So here it will be like this, okay. So yeah, we'll draw in the software more nicely, and this is just I'm explaining what happens, okay. Next is, if both are equal root may happen, okay. If the discriminant is 0, equal root happens. So lambda 1 and lambda 2 are equal and both are negative. So in that situation what happened, in that situation, the fixed point is called a stable star, okay. In that situation the fixed point is called a stable star. So what happened in that situation, let me here also draw one diagram. So if lambda 1 is equal to lambda 2, then this is a fixed point and both are negative, everything is going toward the fixed point. and it is moving in a straight line, not in the curve, it is moving in, everything is moving in, toward the center through a straight line. If lambda 1 is not equal to lambda 2, it may be moving in sub curve form like this. But if lambda 1 is equal to lambda 2 exactly, if it is both are if they are negative, then they will be moving toward the origin like this. So this one we call it stable star. It is like star form, no? Center, everything is converging toward the origin. It looks like a star. So this is, we call it, call it stable star. If lambda 1 is equal to lambda 2 and both are negative, then the fixed point is called stable star. If lambda 1 is equal to lambda 2 and both are positive, instead of moving toward the fixed point in this situation, and it is moving away from the fixed point in straight line, so it is called unstable star. So it is called unstable star. So when lambda 1 is equal to lambda 2 and both are positive, then the fixed point is called unstable star. Okay, and then let us come toward the case when lambda 1 lambda 2 are complex. That means the discriminant is negative. That means stretch square minus 4 times determinant of the matrix A is negative. Then lambda 1 and lambda 2 are complex number. Okay, suppose then if lambda 1 is this one, lambda 2 will be the conjugate like this. Lambda 1 is equal to alpha plus I beta, and lambda 2 will be alpha minus I beta. Both alpha and beta are real numbers. Okay, then it may happen like this: alpha, the real part, is negative. The fixed point is strongly stable spiral. In that situation, what happen? If lambda, if lambda is negative, the fixed point will be strongly stable spiral. So here let me draw one diagram here for, here, again let us draw this one. This is x-axis, this is y-axis, this is y-axis, this is x-axis. Okay, so strongly stable spiral. Suppose if you are starting from this point, then what happen? It is spiraling toward the center like this. Okay, then so ultimately it is going toward the fixed point, the center of the plane. Okay, it is moving toward the fixed point. Okay, so it is strongly, as t tends to infinity, okay, it is moving toward the origin asymptotically. Okay, so that means as t tends to infinity, if you start from here, it is moving toward the fixed point. If you start from here also, from every point, it will be spiraling strongly going toward the fixed point. Okay, so this happen when the real part is a negative number. When the real part of the complex root is a negative number, then the fixed point is strongly stable spiral. Okay, yeah, and just opposite to that, what happen? When alpha is positive, the fixed point is strongly unstable spiral. The fixed point is strongly unstable spiral. Okay, so let us see for that one. In that situation, this arrow will be, instead of going toward the origin, it is moving away from the origin. Okay, it is coming out from the origin like this. This will be the case when lambda, the alpha, the real part of the complex root, is positive number. So instead of coming toward the origin, it will be moving away from the origin. Okay, next, let us see. If alpha is equal to 0, the roots are purely imaginary. Okay, so then the roots are purely imaginary. So what happened in that situation? In that situation, the fixed point is a stable center. Okay, the fixed point is a stable center. How does it look like in that situation? Let me draw the diagram here. Suppose this is your x-axis, suppose this is your y-axis. if the real part is 0, the roots are purely imaginary, mean this is, this is stable center, we call it. If you start from here, so you think about, this is the distance from origin to, this is the radius of the circle, then it will be, the orbit will be like this. Okay, if you start here, the orbit will be like this. It is, it is neither moving away from the center nor moving in toward the center, so it's such type of, fixed point, we call it stable center. Okay, stable center, so it remains in a circular orbit around the fixed point. Okay, it remains in a circular orbit around the fixed point. Okay, such fixed point we call it stable, center. Such fixed point we call it stable fixed point when the real part of the complex roots are, 0, then the fixed point is called stable fixed point, stable center. Okay, so this is all about that one. As I told you, and ultimately the property of the matrix, will determine the nature of the, eigenvalue. If you know the nature of the eigenvalue, just now according to the analysis, we can understand the nature of the fixed point. Is it stable, unstable, stable not, unstable not? Okay, then, center, stable center, stable star. Okay, unstable star, spiral, strongly stable spiral, strongly unstable spiral, all these things, so you can determine. Okay, so yeah, then alpha, the trace is the real part, is the, this is the real part, divided by 2 is the real part, so this will be negative, means trace is negative. Okay, and then this is positive, means what? Alpha is the real part, this is positive, means the trace is positive. Okay, and the real part is 0, means alpha 0 means trace is 0. All right, so if you know the trace and determinant, you can understand the nature of the eigenvalue. So if you know the nature of the eigenvalue, you will know the nature of the fixed point. Okay, so that is all about the, nature of the fixed point according to the nature of the eigenvalue. So let us see some example, simple example. So for this simple example, this is the case of decoupled one. Maybe the system may be coupled one, so ultimately you can decouple it, then it is very simple. Okay, so what are the eigenvalues? Eigenvalue is very simple, straightforward. 2 and 1, they are eigenvalue, they are positive. Okay, so in that situation, let us draw using that software, free software. Let us draw. So dx by dt is equal to twice x, dy by dt is equal to y. Let us see. So in this situation, both the eigenvalues are real and positive, so it is unstable not. It is unstable not. You see the fixed point 0, 0 is the fixed point. See, from the fixed point, it is moving away. The arrow is in this direction. It is moving away from everywhere. Okay, so along the x-axis also, it is moving away. Right, see, it is moving away from all origin. It is moving away, it is moving away. You see, the orbits are moving away from the, from the fixed point. All right, so this is the case. So it is unstable. It is unstable because both the roots are real and positive, so it is unstable. Okay, so such type of fixed point, this is 0, 0 is a fixed point. Such type of fixed point, we call it unstable not. Unstable not. Okay, so what are moving away? The clearly direction of the arrow is away from the origin. Okay, so the solution curve or the trajectory or the orbit, they are moving away from the fixed point. Okay, so dynamics, just looking at the nature of this, phase curves, you can understand the nature, of the dynamical behavior of the system. You can understand. That is the beauty of this, analysis of this study. So next, let us go to another example. Yeah. So this is the case when, this is the case when one of the root is negative, another one is positive. So in that situation, it is called unstable saddle point. In one direction it is coming toward the positive origin, and in another way it is moving away. Okay, so let us see how does it look like in this situation. One root is negative, another one is positive. So that is minus 2x here. It is here minus 2x, and this is y. Let us see. So this is the way. The arrow is very clear, see. So along the x-axis, the first eigenvalue is corresponding to the x-axis. Okay, so along the x-axis, as t tends to infinity, it is moving toward the origin. You see from the arrow, from here also it is moving, from here also it is moving, here also it is moving. But along the y-axis, since it is positive eigenvalue, it is moving away from the origin, tending toward the infinity. From here also negative infinity, like this. All right, so then let us see here. See, the phase curve is like this. Okay, phase curve is like this, so it is like this, and then from here it is moving away, moving in x-axis, moving away from y-axis. Okay, so phase curve is like this. So it gives you lots of information of the dynamics. It is never coming toward the fixed point. Such type of fixed point is called saddle point. Unstable. Saddle points are unstable. Saddle points are unstable. Okay, so this is the case of one negative eigenvalue, another positive eigenvalue. All right, so if the first eigenvalue is positive, second one is negative, just nature is similar, just the reverse one. In this direction, this is going away, this one from this direction, coming toward the origin, like this. Okay, so nothing much different is there. You can see lots of example yourself, and then try to understand. So next is another example. Let us see. Both are negative. When both are negative, it is called stable knot. Okay, when both are negative, it is called stable knot. Let us see, -2 and -1. The first eigenvalue is -2, the second eigenvalue is -1. When it is negative case, let us see. First, let us see. You see, so if it is both are the negative, then you see the direction field, all are directing toward the center. Okay, suppose if you start from here, see, it is moving toward the fixed point. You again start from here, it is moving toward the fixed point. Everywhere from the phase space, ultimately the orbits are converging towards the fixed point. All right, so fixed point is important for the studying dynamical behavior. So it is moving toward the fixed point. You see, here also it is moving. Right, so here also, everywhere it is going toward the fixed point. Okay, so this is the case when all the eigenvalues are negative. All right, so next let us see this one. This example, let us see. Dx by dt is equal to x minus 5y, dy by dt is equal to x minus y. So what is the eigenvalue of this one? What is it? You find out, try to find out what is the eigenvalue, and look at the nature of the eigenvalue. Most probably this will be, I think, complex root. Okay, so let us see this example, x minus 5y, x minus y. In this case, x minus 5y minus 5y. Then the second one is what? Second one is x minus y. So x minus y. Yes, x minus y. What happened then? Yes, see, this is the case. This is the direction field, and let us see what is the curve. Okay, like this. Both are, it looks like it is yeah, it is moving toward the that this is the case when the real both the roots are complex number, and the real part of the eigenvalue is negative. It is spiraling in. Okay, the arrow is toward the origin. All right, so spiraling in. Yes, it is like this. Okay, so it is spiraling. Okay, start, then you reduce the radius constantly, and then since it is a negative, the eigenvalue, real part of the eigenvalue is negative, so it is reducing the radius is reducing, means when the radius is reducing, this is spiral, so it is going toward the fixed point. Okay, that is the center of the phase plane. Okay, phase curve. So origin or center of the phase plane is the fixed point. It is moving in toward the fixed point. Okay, every orbit is moving in toward the fixed point. All right, so this is the case. So next let us see, and this one we have done. How about this one? And most probably here the yes, from here you can easily see that what is the trace of the matrix. This is the first coefficient 1, the second coefficient like that, trace is 0 in this situation. So let us see here this one. Let us see the fifth example. 2x minus 5y x minus y. 2x minus 5y x minus y. First you clear all the cup. 2x minus 5y x minus y, is it? Let me see. 5y x minus y. Yeah, let us see. So it is like this. Okay, so let us look at, it is moving away. See, it is moving away. If you start from here, it is moving away. If you start from here, it is moving away. So spiraling, it is going out from the fixed plane, and this is unstable. Okay, if the real part of the complex root is positive, it is spiraling out. Okay, and the fixed point is not stable. All right, so this is the case. So like this you can see lots of example like this. This is the case when it is center stable unstable star. This is the case when it is stable star, like this. All you can see. So many example you can construct yourself. You can see next time also I will give you more example. Okay, so this is how the nature of the fixed point is determined by the nature of the eigenvalues. Okay, so this much today I want to give you, and this is also very important. Next time I will give you some more example